Okay, this is the final video for our Strength of Materials class. It covers Chapter 20, in which we look at pressure vessels, specifically cylindrical pressure vessels. So imagine I have a cylinder, and it is pressurized. Something inside of it, typically a gas, is compressed, and that compressed gas is wanting to push out against the edges of the cylinder in all directions. What we want to be able to do is calculate the stress in the wall of this pressure vessel and therefore potentially design the thickness of the wall. So the first thing we have to check when analyzing a pressure vessel is to make sure that it is a thin-walled pressure vessel. The reason is we are assuming that the walls of our pressure vessel are very thin, and when they are stressed, when pressure is applied from the inside out, it puts the skin or shell of this vessel in tension. If it was thick, if we had a real thick outside layer here, it could actually bend, and we could be dealing with bending stresses, which is more complicated than what the scope of this class covers. So we have to make sure that we are dealing with a thin-walled pressure vessel, and so there has to be some sort of a cutoff point. And that cutoff point is that the thickness of the wall of the cylinder needs to be less than 0.1 times the radius of the cylinder. So our cylindrical pressure vessel has a radius r, and we want to make sure that the thickness of the pressure vessel, T, is less than 0.1 r. If it is not, if the walls of the cylinder are thicker than that, then the equations that we're about to discuss do not apply. And as I said, the complexity of the problem then becomes beyond the scope of this class. So that's the first thing we need to check to make sure that applies. Then, once we have verified that we have a thin-walled pressure vessel, we have to think of basically the two different ways that we can slice through a cylinder through its center, and that would be to slice through it horizontally or to slice through it vertically. First, we're going to look at this vertical slice. If we slice through a cylinder vertically, we'll cut it into two halves. I'll try my best to draw a isometric drawing here of half of the cylinder. And then we've got the other half of the cylinder over here. So we've sliced through it vertically, and what we see here is that the walls of the cylinder are essentially two long rectangles, and we can describe them with a length L and a wall thickness of T. And so the pressure acting out, let me draw our cylinder from above, and we've sliced through it horizontally. That pressure is acting out in all directions. Okay, so we have a bunch of little force vectors acting out. Some of them, well, there'd be like one right here, theoretically, that's perfectly vertical, and maybe one down here at the bottom that's perfectly horizontal. And all the others in between are somewhat diagonal, so they have a little bit of a vertical component and a little bit of a horizontal component. If we were to add up the vertical components of all of these force vectors, we can say that it's pushing up with a total force, a combined force of all these vectors of P. Big P is the force pushing up. And so that force is going to be resisted by this wall and this wall, these two walls here, the outer walls of the cylinder. So the stress, and the book uses an alpha in this chapter to describe this pressure vessel stress, is equal to the total pressure P, or the total force P, divided by 2, divided by this wall and this wall. So we've got P divided by 2. That's the pressure acting on one of these rectangles. And then we're going to divide that by the area of that rectangle, which is the thickness. Not divided by. Let me back that up. But thickness times length. Okay? And so we can do a little bit of rearrangement of the formula. We could say, instead of P over 2 in the numerator, this is P over 2TL. And then we can replace the big P here, which is a force, with what that force is, where that big P comes from, is all of these little pressures, P, all these little P's, acting on an area. I'm going to change my marker color here to shade in the big area, the big cross-sectional area of our cylinder. So if we have this force acting on this rectangular area, which is going to have a width of D, we'll call that big D for diameter of the cylinder, the pressure times area will give us the force. So we're talking a little p pressure times a big D diameter. And we can put a little subscript I on that to represent the inside diameter, divided by, and the area of the rectangle is not just D, but D times L here, our length. So P times DL is the pressure times this area, divided by 2TL. And then the L's cancel out, and I'm left with P times DI over 2T. So this is the formula we use. Alpha equals P times DI over 2T for finding the stress. Let me change my ink color once more. On these vertical walls of the cylinder, resulting from the interior force pushing out when we slice through the cylinder vertically. Okay, this is called hoop stress. So it's sometimes referred to as hoop stress. So it is the stress in these vertical walls, and this is the formula for it right here. Now let's scroll down here. I'll redraw a new cylinder. And let's imagine the other way in which we can slice through a cylinder, and that through its center, and that's horizontally. If we do that, we end up slicing through a cross-section that is a hollow circle, basically. And so this time, in this direction, our big P, the pressure pushing out, is acting on this area, which is the area of the inside circle. So big P is equal to little p times the area of a circle, pi d squared. And we're talking about the inside diameter here. No, it would be pi r squared. Pi d squared, it would be, radius is d over 2. So we square the d, we square the 2, and so this is 4. So it's little p times pi times inside diameter squared over 4. Gives us the force acting in this direction. Then to find the stress, we would need to divide it by the area of the cylindrical wall here. Okay, and a way we can approximate that is if we were to basically cut this circle, and this circle that's made up of the exterior wall of the cylinder, and unroll it, we would end up with lay it out flat basically, we would have a rectangle whose height is t and whose length is equal to the circumference of the cylinder, and the circumference is equal to pi d. So the stress is going to equal P times pi d squared over 4. And then we're going to divide that by T times pi d. Okay, so what happens here if we simplify this mathematically is we still have the P, the pi and the pi cancels out. The d and d squared leaves us just d, and then the 4, because it's on the denominator, we can move it down to the denominator down here, and then we still have t. So this is the derived formula for the stress in the other direction. This stress we call longitudinal stress. So that's our longitudinal stress. So if we look at our two equations here, we have two different stresses. We have the stress for what we call hoop stress, or it's also called circumferential. I think I spelled that right. No, circumference. I forgot an E in there. Okay, there we go. Circumferential stress, and that is equal to P times di over 2t, where this is the interior pressure, the inside diameter, 2 times the wall thickness. And then we have the longitudinal, which is acting in the opposite direction, and that stress is equal to little p times di over 4t. So you may recognize that these formulas are very similar to each other, with the difference of this is a 2 and this is a 4, which means the longitudinal stress is always exactly half of what the circumferential stress is. So when you're designing a thin-walled cylindrical pressure vessel, we're not so much concerned about the longitudinal stress because it's always less. We want to design for worst case scenario. So for design purposes, we only need to concern ourselves with the hoop stress or circumferential stress. And so getting pretty close to my time limit here. These two equations are really the only two equations we need to know in this chapter. So we've kind of looked at where they come from, and we will put them into practice by solving an example problem in the next video.